I will begin. This is distributed consensus for safe two-spacecraft autonomy. And I'm going to try to go very fast and high level because I have to go at 4:30. So this is something I did a month or two ago as like a side quest for a paper that we're writing for visors, and I thought it was interesting, so I wanted to share about it. This is not in preparation for any particular conference or paper or anything like that, so interrupt if you like. It's casual. Okay, so as Shane says, typical presentation structure, motivation, background, problem, solution, results, hooray. The motivation for this work, distributed autonomy for controlling mostly pairs of spacecraft, but generalizable to other missions. The real thing where this is a real kind of mission where this is applicable is if you have distributed control, distributed autonomy state machines between spacecraft that need to be coordinated safely in the presence of communication failures. So this is a type of control design for missions that's still kind of rare, but it's starting to be seen in things like visors and Starry. I put Proba 3 on here because it's close, though they just have kind of fully coupled planning on a single spacecraft. So they're not exchanging control back and forth between two different spacecraft. Sorry, not control, but planning. But it's the kind of mission where you might want to have robust autonomy on both spacecraft. So this presentation will focus on visors as the motivating use case, but any kind of mission where you're doing distributed decision-making is applicable. So to review the driving requirements here for visors is we want spacecraft to never both be active because our whole control design relies on doing relative control planned on a single spacecraft. So if both spacecraft are trying to plan relative control, you could end up in a mess. But we want either spacecraft to have the ability to be active so that we can have robustness to failures on one spacecraft and double the mission lifetime in terms of delta V. We want to be tolerant to propulsion failure on a single spacecraft at any time. We want to still have some action from the passive spacecraft. So even though it's following, it still needs to take actions in sync with the leader spacecraft. And we need to be tolerant of intermittent cross-link blackouts at any time. So we don't have reliable communication between the spacecraft, as is pretty much always the case if you're using radio. From these, we imply a few key ConOps of the visor's mission. One is autonomous role switching. So we need the ability for spacecraft to say, oh, something's gone wrong with my prop system. You take over in the middle of autonomous ops. And we need to provide certain guarantees despite failures in communication. This is the visor's ConOps. There's a bunch of state machines. Do not understand this. The point is just there's a lot going on in the autonomy for visors where it has to drive itself through a bunch of autonomous ConOps. But all of this is designed assuming that one of the spacecraft is in control of things, right? So this is just the ConOps saying someone's leading. What should we do next? Not what happens if we have to change leadership from one spacecraft to the other. So role switching is the process of actually taking the state machine from one spacecraft and saying, okay, now the other spacecraft's going to start running the state machine. As an example of what can go wrong if you have unreliable communication trying to do something like this, race conditions, as they're called in distributed systems, the outcome might depend on subtle orderings between things happening from different sources that don't have a shared clock. So if spacecraft 1 says, I need to role switch to spacecraft 2, spacecraft 2, you become active. I'm yielding. You become active. And at the same time, ground operators say, hey, actually, we've realized something is wrong. We're going to switch to a different mission level target with spacecraft 1 active, because when we command the formation, we say which spacecraft we want to be active. Spacecraft 2 might receive one or the other of these commands first. Spacecraft 1 thinks one thing, spacecraft 2 thinks the other thing, and they don't necessarily stay in sync. There are many ways to resolve this, but it has to be something done intentionally and carefully, or you can end up in situations where they are not acting in coordination. Then there are many other examples of race conditions that could be possible. Okay, some background distributed consensus algorithms from CS, database, networking theory. In general, there's no way to totally order or synchronize distributed systems. People have invented a lot of algorithms for coordinating the communication between them. And they have to juggle this reality of unreliable communication and still provide some sort of guarantees about the behavior. So there's a rich world of literature for especially databases where you have many nodes in a distributed database and you want to never lose data, things like that. But we're interested in applying that to spacecraft and the unique aspects of spacecraft. So for distributed communication that may be unreliable, the typical model that is used is to say, okay, each actor or kind of disparate source, that's all kind of has reliable operation within itself, can send messages back and forth. Um, and the messages take some time to arrive, and the happens before relationship in this kind of model is not a total order. So there may be pairs of events for which there's no clear meaning of one happens before the other. The example here would be this one and this one. We can see in this sort of like absolute view of time, okay, it looks like this one's a little higher up in the diagram, so it happens before. But from a communication and system behavior sense, this event does not happen before the other because the receipt of this packet had not happened before this one did. So, there's no absolute sense of time in the universe, so to speak. Depends where you are, and propagation delay is a real thing. So you have to contend with this. Then perturbations to communicating systems, like we would simulate perturbations to orbit dynamics, for example. Messages can be dropped if they're not received with a high enough signal to noise ratio. They may be delayed. This is more common in terrestrial networks where you have complex queuing buffers and things. But it still can be the case if you have a spacecraft radio that has a complex implementation and may have buffers where messages get stored before they can be successfully delivered. And messages might be duplicated, especially if hardware transmission layers try to themselves take, assurance for saying, oh, I'll make sure at least one copy gets delivered, which is sometimes the performance spec that radios try to follow. So applying this to visors. In some ways, this is a simpler system with only 2 nodes, but in other ways that makes things harder because in general, you can't have complete fault tolerance with only 2 nodes. Because if the leader suddenly goes away or stops communicating, the follower has no way of knowing what happened to it, whether it's still controlling, whether it thinks it's still controlling. So it can't safely take over. And this means that in the worst case, both spacecraft stop autonomously controlling. We can still provide other guarantees despite that. So we can try to guarantee that both spacecraft are never active, which we really care about, that they're robust to communication failures, but we accept this cost of like, okay, sometimes both spacecraft may become passive, and we just have to be okay with that. We can solve that by using passive safety in our control design so that we're tolerant to, okay, if at any time we just have to stop maneuvering, that's what passive safety is for. An interesting connection here, if you've ever taken any CS classes, you may have heard of the CAP theorem. It's very famous in distributed systems design, and it says you can only have 2 of the 3 properties: consistency, availability, and partition tolerance. And in this particular design and safety trade-off, we're choosing to sacrifice availability. We're saying actually there might be a time where neither spacecraft can be in service in order to have consistency and partition tolerance, meaning if you cut communications between them. Okay, all that background, problem statement. For visors, we need to create and verify an algorithm for coordinating the communication between the spacecraft and the ground systems to facilitate autonomous role switching, ground-commanded role switching, state synchronization, such that despite any amount, asterisk, of dropped, duplicated, and delayed crosslink messages, we're guaranteed to eventually end up in the same state regarding autonomous control, and we will never, ever simultaneously have the 2 systems try to perform autonomous control. The asterisk is if you have complete, every message is dropped, obviously you cannot satisfy this property of the eventually agreeing. But as long as you're less than 100%, eventually you will agree on the same state. Might be a long time, but eventually. Okay, solution: consensus algorithm and verifying it with discrete event simulation. So I'm going to try to just give an overview of what is going on here. The consensus algorithm is like a lot of nitty-gritty details, or it doesn't work correctly. So I'm going to give an overview of some parts of its functioning, but the whole thing, if you're interested, go read the source code. It's in the flight software repo. But we're basically looking to make a synchronization component that will be part of the visor's flight software, where we can have an autonomous state machine, use my mouse, we can have autonomous state machine on either spacecraft that interacts with the synchronization component, and the synchronization component handles exchanging of crosslink messages between the other spacecraft and the ground systems, such that the state machine on each spacecraft can kind of just assume it's in a nice, well-behaved world. And I can say, I'm just running my stuff. Oh, I was told to become active. I was told to go to this state. I'll just do my thing. And then the synchronization component will handle ensuring the other spacecraft gets up to date with all of that. This is the interface for it. Like I said, there's a lot of hairy details and visors, but for the rest of this presentation, I'm just going to focus on one of the key aspects or roles of the synchronization component, which is this active-passive target switching between the spacecraft. So in the inputs to the synchronization component or algorithm, we get commands from the ground systems saying, hey, go into this formation state, one or the other spacecraft controlling. On the outputs of the synchronization component, we want to tell the onboard state machine, whether it's active or passive, what it should be trying to do. And we exchange cross-link messages in order to be able to do that. Some examples of like the fundamental things, that the tools that you use to build a consensus algorithm. The first is acknowledgements. So if someone says, oh, here's new information, you want some way of replying saying, yes, I got that information, so that the sender knows that it was successful. Otherwise, it might need to retry or do some other action. An example of this being used to respond to dropped packets. If spacecraft 1 says, here's some new information, it doesn't get delivered, it won't ever hear an acknowledgement for that, so it can try again until it gets an acknowledgement. The other kind of fundamental or foundation for consensus algorithms is sequence numbers. This is used all over the place. And you kind of mark any given thing that you send with a number that you both agree we're only ever going to increase when there's new information. And this way you can tell if things have gotten reordered or if you're getting a delayed or reply to something that you sent a long time ago, for example, or a duplicate of a packet that was received a long time ago. Okay, probably, what time is it? 22. Okay, I'm kind of just going to skip through this. I was going to go through some pseudocode of like what kind of things the algorithm does. And again, this is itself even only a very small part of it, but basically it was going to walk through what happens when you receive a command from the ground, what happens when you receive new information from the other spacecraft, what happens when you receive an acknowledgement. Here's the pseudocode. This is not literally what it looks like in the code, but it's pretty close. I tried to make it more self-contained. You can scan over it. If we have time, I'll come back to this and look at detail. But the gist is you want to check if the sequence numbers are increasing, decreasing, ignore the things that shouldn't be accounted for, make sure you retransmit things that don't get acknowledged, things like that. This is when you receive new information from the other spacecraft. An interesting thing that's specifically for this spacecraft active-passive fail-safe sort of mode is that we say, where is it? Bias accept. So this is not something you would necessarily need if you assume that the ground systems are like always behaving perfectly. But if you want to be robust to actually conflicting commands from the ground system, so just like be extra safe, the spacecraft will always ensure that they don't even both become active, even if the ground system sends them two different packets with the same sequence number saying you should be active. We can use this to say, basically bias towards accepting if the new command is to not be active. And so then when we bias accept, we check if our new sequence number is just less than the last one that we had. Otherwise, we check if it's less than or equal to the last one we had. And this will override the state towards the passive mode in case of conflicting information, right? So it's just a tiebreaker that says, if you're told to both be active and be passive, bias towards being passive because that's the safer thing to do. I'll skip over this and skip over that. Okay, verification. So I used discrete event simulation, as you guys probably know I love, to verify this. So wrote a simulation, discrete event simulation orders events on a timeline. It's a dynamic timeline. You can add events as the simulation progresses. They all get ordered and executed in order. And this is great for modeling the delivery and noise and crosslink messages, because you can give any message a random delay, you can drop some of them, and they'll all be processed kind of in order as they would be processed in real life. So our kind of noise model here for crosslink messages is that we can have some probability of just dropping them, and we can have some continuous distribution for the delivery time of messages. And then we just need to specify a bunch of test cases and say, okay, in each test case, let's schedule some like initial inputs to be sent to the spacecraft. So these would generally be like commands from the ground. And then we simulate the system until it reaches a steady state, like there are no more events, basically, meaning that both spacecraft are happy. They don't want to do anything more. Then you check if all the desired properties that you wanted to hold. So I'll go through 3 examples of test cases. I think in total I wrote 13 test cases, which I'll scroll through, but this is 3 of them. So this is kind of easy mode. Ground tells the first spacecraft to begin autonomy with itself active. At the end, both spacecraft should agree that that's the case, and they should never both be active simultaneously. Normal mode. Ground tells spacecraft 1 to become active. Then after a little bit, it changes its mind and immediately tells spacecraft 2 to start autonomy with spacecraft 2 active. At the end, spacecraft 2 should be active, spacecraft 1 should not, and they should never both be active at the same time, no matter what messages got dropped or delayed. Hard mode. Defective ground system simultaneously sends conflicting commands to both spacecraft, telling them both to become active with the same sequence number. Invariance. You don't really know what the desired state should be in this case. Maybe one or the other is active, or they're both passive, but no matter what, they should not both become active simultaneously. Okay, results, demo. So where's my VS Code? Okay, so first thing to show, while I was developing this, I basically made this like little tool that will show the results. So I'm just running that right now. And this will just cycle through a bunch of very aggressive, like terrible communication cases and ensure that the desired properties are held throughout all of them. So this is basically the first case. And you can basically random sample a bunch of executions of the algorithm. Probably to give a sense of what it should be doing, we want to make things perfect. So we can say, okay, no chance of dropping the crosslink. So this is basically the noise model for crosslink. So we can just say, okay, with 0% chance, drop a crosslink message. Sorry, I should say with 100% receive the crosslink message, and no delay. And if you do this, then okay, here's the like most basic execution of the algorithm, right? So ground tells one spacecraft to become active. It checks with the other spacecraft. It says, yes, you're good. Then the first spacecraft becomes active. That's the gist of it. Another case is, okay, the one where ground changes its mind and then a little bit later tells the other spacecraft to become active. You can see this perfect execution says first spacecraft becomes active, then the second spacecraft becomes active, yada, yada, yada. And then conflicting command, looks like here in the perfect execution, neither spacecraft becomes active, so that's fine. But if we go back to kind of the noisy case where we have very aggressive, 50% of packets are dropped and log normal distribution with like, up to multiple seconds of tail, we still hold all the desired properties amidst crazy executions. So this is just a visualizer giving a sense of what they look like. You can see in the conflicting command one, sometimes with the noisy case, one spacecraft does become active, but we never have them both be active at the same time. And this is like the visual form, but ultimately I wrote a bunch of these cases, and so they're pretty compact. You can see them documented here. So all of these are like, okay, when the sim starts, we're going to send a command to one spacecraft or the other. We're going to run stuff, and then we're going to check invariance at the end. Wrote a bunch of them, and then at the end, I said, okay, let's run 1,000 of each of those. And you can run 1,000 of each of them, and then it says, okay, ran 13,000 successful cases. And that's just checking that all of these checks and invariance passed in every case. So we can go into the synchronization algorithm and just to prove that, okay, all of this stuff has to be done correctly. Let's find the classic, let's find like a less than and change it to a less than equal, or find a less than equal and change it to a less than. Okay, I was like on one here. So this line, less than, if you change this less than to a less than equal, at least one test will not fail, will not pass. So, okay, you get an abort in the unit tests and you have to hop in and debug that. Let's find another. Okay, this one, less than equal. Yeah, that doesn't work. So this is just saying that in at least one of these cases, if the algorithm was not, exactly right, and like maybe more of this here. Yep, or maybe we undo this and return 0 instead of a 1. Yeah, that doesn't work. But if everything is just right, then you successfully end up in the right case, all of these 13,000 different random trajectories that you checked. And so let me put this back to 10 and just show this kind of like cycling through all the 13 different cases that was used. I'm only showing 10 of them here, but these are running dynamically like as I cycle through them, so you could simulate as many of these as you wanted. And this doesn't offer a guarantee. So in my limitations future work, testing with simulation like this gives confidence, and it supports fast development, but it's not a formal guarantee of correctness. So if the stakes are high, you should use formal methods on the source code, static analysis, computer-assisted proofs to ensure like actually, yes, guaranteed, assuming that your CPU is working correctly, you'll never end up in a bad state. Then the other limitation is this current algorithm only accounts for communication failure, not like a complete loss of state on your spacecraft. So that's kind of work that still needs to be done to ensure that even in case of a bus reset, like if one spacecraft loses all notion of where it was kind of in the sequence of communication, that you could somehow recover and restore operations in a somewhat graceful and at least not dangerous way. So that will require more testing and possibly refinement of the algorithm to do that. But that is the whole thing. Any questions?